Thank you, everyone. So I'm here presenting on behalf of Yusuf because unfortunately he had another commitment, but he did send his warmest regards to all of you here. So my name is David Tabarat. I'm part of the solutions engineering team from Indonesia, and right now I'm trying to presenting these topics, which is LWD data acquisition. In regards of the caliper and drilling mechanics also. As a new approach for the geothermal drilling operation. This is a case study from one of our well in Indonesia, specifically in Sumatra. Okay, before we go deeper into the analysis, let me introduce you a little bit about the LWD system, right? So basically, this LWD stands for logging while drilling. Is simply combine the conventional wire and log into the drilling BHA. So you can have more efficient operation where you do not have to pull out the hole and then running the wire and log, right? So you can run simultaneously using the drilling BHA. So in here, this is the typical very basic LWD setups that we can run in the geothermal wells. The red one is the standard MWD. We call it MWD because it's measurement while drilling, basically only transmitting the wellbore survey data downhole, right? Consisting of the measure depth, inclination, and azimuth. This is the MWD part. And then on top of that, we also add the PWD, or annular pressure while drilling, where we can also check or see the ECD, the equivalent circulating density. And then on top of that, also we can also include the vibration sensor, right? Where we can see the modes and the mode shape of the vibration downhole. And then lastly, we can also include the temperature collar or temperature sensor into the drilling BHA. Okay. In LWD service specifically for the geothermal, we are using this electromagnetic telemetry, right? So why we are using this one, the electromagnetic, because of we have two different things, two different telemetry system. We can use this mud pulse system, which is we are using the differential pressure of the mud inside of the string, and then we can have this electromagnetic. So why we are using this electromagnetic? Because of in geothermal well, we are seeking for the low circulation, right? Because that's basically the potential fractures of the reservoir. So this this electromagnetic, it's much more independent in terms of the return flow of the mud, right? So once you hit the total losses and you start mixing fresh water with air, mixtures of air, this EM is still can have data from downhole, right? So basically this EM having two antennas, the surface antenna in surface, and then downhole antenna. We will get into the details of the BHA itself. Okay, so I'm speaking of the case study. So this is the well architecture of this case study. So basically this is, we are having 4 different hole sections starting from 26 inch, and then we're kicking off in 7.5 inch BHA up to 30 degrees inclination, and then we drilled with 12.25 here, and then 978 as the last hole section until TD. The blue line represent the plan, and then the red line represent the actual trajectory, right? So in this well, where we use the LWD is on the 12.25 hole sections. These yellow lines represents the area we run these LWD tools. So this is the side view of the well, and then this is the top view of the wells. If you can see, the blue as the plan, and then the red is the actual one. Okay, I'm gonna jump into the configuration of the LWD tools. So basically in this well, we are using the mud motor BHA, right? And then on top of that, we have float sub and stabilizer. So this small figure is just like simplify the figures of the tools below our LWD. So on top of our motor and stabilizer, we also have this acoustic caliper collar. We call it ACAL. And then PWD stands for the pressure while drilling. And then the ADSIM, our processor. And then on top of that, we have our PCDC or directional sensor, right? On top of that, we have this EM antenna sub, where this one is part of the EM telemetry things. Okay, With the typical sensor distance, the PWD, this one is around 18 meters away from the bit, and then acoustic caliper is around 15, and then VCDC around 22. Sorry, in feet, 22 feet. Okay. So I'm going to jump into the first analysis, which is showing the caliper data analysis. Like I mentioned to you, we are running this acoustic caliper. So basically, this acoustic caliper sends signal like acoustic impedance to the formation, and then record the time travel between transmitting and then receiving, right? So that happens in milliseconds. So all of this data spreads represents the feedback in milliseconds of the acoustic signal, right? So all of this you can see it's all scattered, but if you can see here, the gray line is the average one, right? So by this we can conclude which are the correct data, right? So if you see here, this is the 12 and quarter whole section. We can set that one as a 12 and quarter whole sections plus minus, and then all of this one is the noises that the drilling condition made. So after we have standardized or bench the errors, right? So we can also filter out. So by this, we can filter out the actual conditions during drilling, right? So on the left-hand side, this is the real-time data from the acoustic caliper, and then the right-hand side, this is the one that we have filtered out based on this statistical data analysis, right? If you can see, in the real time, we have a lot of noises. That's why it's showing like very, very scattered. And then after filtering out and screen out using this methodology, we can see it's quite smooth, right? So you can see a couple of interval that severely overgauging or wash out, right? So by this also we can get data. The average hole size indicator is around 13.3, which indicates we have, in average, we have like overgauging around 1 inch because the bit size is 12 and quarter. Okay, the second thing is the drilling mechanics data analysis, right? So like I mentioned to you before, we are using the EM. But as only for differentiation, the 7.5 inch, we are using the basic EM. If you can see here, using basic EM, the PWD data or ECD data is less dense compared to the 12 and quarter, because in 12 and quarter, also because we have our HSIM or processor, we are using this EM PPM, much more higher data rate compared to the previous sections, which is 7.5 inch. So if you see the comparison for the ECD itself, it was like more dense and then more details compared to the previous hole, right? So this is because of the EM PPM that we use in the 12 and quarter hole sections. Okay, the next one, we also looking into the vibration, right? So some of you may know the vibration methods or modes consisted of 3 axes: the lateral vibration, the torsional, and the axial vibration. By these 3 different axes, we can see 9 different type of vibration in here. The combination of the axis and then the frequency where the vibration happen. Right? So that's the basic one. So we also develop our own system, which is, we call it the traffic light system. Green, yellow, and red. Right? The green represents we are in a safe condition. The vibration is quite low. The yellow is intermediate, and then the red one is quite severe or high. Okay. So, So by having this traffic light system, we can easily identify along the whole interval in here, where's the spot that we have like high and very high vibration, right? If you can see here, we divide it into 6 different sections or area. Sections 1, 2, and 3, it's relatively quite low, but we see some high vibration in here, but it's still relatively low compared to the section 4 and section 5, right? Because the magnitude you see the magnitude is quite different, and then this is one is quite high compared to the section 1, 2, 3, and 6. So that's why we start putting attention to these two different part of the formation, which is number 4 and number 5. Okay, I'm going to go into the methodology framework of this analysis or study case. So the methodological framework we separate into 5 different process. The first one will be the formation identification, where we see the formation lithological by doing the MEB or methylene blue test, right, to check the reactivity of the formation. The second is the distribution of the drilling parameter, where we map the parameter that we input and then the result or the parameter output, which is ROP, vibration, and so on and so on. The third one will be the statistic, where we also see the statistical data where the vibration is happen and then the spreadness of the vibration. The fourth one will be the burst file, where this one is the total data of vibration that we receive from the downhole, and then the vibration mode we can conclude from the burst file data. Okay, like I mentioned to you, we put more attention in details for the formation number 4 and number 5, right? Because we see the magnitude of the vibration is much more higher in these two parts of the interval, right? Okay, so we apply the methodological framework, right? First one, we identify what the type of formation, and then we also include the MEB test, right? And then the second one, we see also analyze the drilling parameter and then vibration distribution. The third one, the ROP and vibration statistic. If you can see, the average and peak is quite green, but the torsional surprisingly red, right? So by this, we can conclude the type of vibration, right? So mainly in these two area, we see or we expect to have this torsional resonance or beat chatter. Okay, and then we also looking into the caliper data analysis in terms of the subsurface thing. If you can see here, we also separate that one into 4 different area because we see the severity of the overgauging hole, right? So by this we can conclude area A, B, C, and D having like quite severe of overgauging, right? So correlate with the formation, what type of formation? The formation A, apparently the lithological is intrusion, and then formation B, C, and D is more related with altered volcanics, and the lithology is silicic tuff, right? So we can see where is the typical wellbore breakout happen in terms of the lithology. Okay, so by that, the result is, after we see the vibrational responses compared to the drilling parameters, right, we can optimize the drilling parameters. For example, this XXE05 in here, we reach more higher ROP compared to the offset wells, which is XXE02 and XXE03. Why is that? Because we are confident to put more weight on bit. So in offset well, we play around 20-25 kilopounds because of the vibration and so on and so on. But in here, after seeing the response, we are confident to put up to 30, right? So that's why we can optimize the drilling parameter and then get more ROP. That's part of the improvement because of these vibrations sensors, right? And then for a future application, we also realized that during drilling, we only have one stabilizer just below the acoustic caliper collar. So that's why all the noises that we see before, that's coming because of this poor stabilization, right? So for the future sake, we also plan to have like additional stabilizer on top of the acoustic collar, so we can also reduce the noises during drilling, right? So for the summary, so this methodological framework is provide us valuable data, right? The first one will be the drilling parameters in summary, right? What is the input and then what is the response for the output? And then the second one is the vibration phasous characterization. So we can easily see what type of vibration during drilling, right? The third one is the subsurface insight in regards of the fractures and then the presence of the smectite clay. So maybe some of us know smectite clay is quite dangerous because it can easily react with the fresh water, right? And then the fourth one, it's also giving us insight on the problematic geothermal intervals. Okay, so another summary and the future potential enhancement. The first one will be the drilling parameters roadmap, because in here we can see and benchmarking the drilling parameter in terms of the vibrational and then downhole calipers data. And then the second one is the effective real-time display for the vibration and PWD readings. The third one, the vibration methodology framework can be enhanced also. And then at the same time, we can improve also the borehole drilling strategy, right? So as we know, the discussed case study is discovered in particularly altered volcanic formation, which is related with desit and silitic tuff. And this also bringing value to a first step to become machine learning or AI, right? In conclusion, for the LWD trial in XXC05, it's given us a good result, both for the real-time transmission and recorded acquisition. And then the EM/PPM telemetry given us a very dense data rate for LWD data. And then we still have room for improvement for the BHS interiorization and time filter traveling. Okay. And then for this LWD data can be analyzed for both drilling operation and then subsurface analysis. The last one, in here, this case study is very important for us because it's open up the feasibility of hazard mitigation in terms of cost saving from potential stuck pipe because of this problematic zone. Okay, I think that's all from my presentation today. Any questions? Oh, is it clear enough? Okay. Okay then. Okay, so thank you. Thank you, everyone.
Thank you so much for that wonderful presentation.